Claims require extraordinary evidence. And it is my job, my responsibility as an astronomer to remind people that alien hypotheses should always be a last resort. Now, I want to tell you a story about that. It involves data from a NASA mission, ordinary people, and one of the most extraordinary stars in our galaxy. We began in 2009 with the launch of NASA's Kepler mission. Kepler's main scientific objective was to find planets outside of our solar system. It did this by staring at a single field in the sky, this one with all the tiny boxes. And in this one field, it monitored the brightness of over 150,000 stars continuously for 4 years, taking a data point every 30 minutes. It was looking for what astronomers call a transit. This is when the planet's orbit is aligned in our line of sight, just so that the planet crosses in front of a star. And when this happens, it blocks out a tiny bit of starlight, which you can see as a dip in this curve. And so the team at NASA had developed very sophisticated computers to search for transits in all the Kepler data. At the same time of the first data release, astronomers at Yale were wondering an interesting thing. What if computers missed something? And so we launched the citizen science project called Planet Hunters to have people look at the same data. The human brain has an amazing ability for pattern recognition, sometimes even better than a computer. However, there was a lot of skepticism around this. My colleague, Deborah Fisher, founder of the Planet Hunters Project, said that people at the time were saying, "You're crazy. There's no way that a computer will miss a signal." And so it was on, the classic human versus machine gamble. And if we found one planet, we would be thrilled. When I joined the team 4 years ago, we had already found a couple. And today, with the help of over 300,000 science enthusiasts, we have found dozens. And we've also found one of the most mysterious stars in our galaxy. So to understand this, let me show you what a normal transit in Kepler data looks like. On this graph, on the left-hand side, you have the amount of light, and on the bottom is time. The white line is the light just from the star, what astronomers call a light curve. Now, when a planet transits a star, it blocks out little bit of this light, and the depth of this transit reflects the size of the object itself. And so, for example, let's take Jupiter. Planets don't get much bigger than Jupiter. Jupiter will make a 1% drop in a star's brightness. Earth, on the other hand, is 11 times smaller than Jupiter, and signal is barely visible in the data. So back to our mystery. A few years ago, Planet Hunters were sifting through data looking for transits, and they spotted a mysterious signal coming from the star KIC 8462852. The observations in May of 2009 were the first they spotted, and they started talking about this in the discussion forums. They said an object like Jupiter would make a drop like this in the star's light, but they were also saying it was giant. You see, transits normally only last for a few hours, and this one lasted for almost a week. They were also saying that it looks asymmetric, meaning that instead of the clean U-shaped dip that we saw with Jupiter, it had this strange slope that you can see on the left side. This seemed to indicate that whatever was getting in the way and blocking the starlight was not circular like a planet. There are a few more dips that happened, but for a couple of years, it was pretty quiet. And then in March of 2011, we see this. The star's light drops by a whole 15%. And this is huge compared to a planet, which would only make a 1% drop. We describe this feature as both smooth and clean. It also is asymmetric, having a gradual dimming that lasts almost a week, and then it snaps right back up to normal in just a matter of days. And again, after this, not much happens. Until February of 2013, things start to get really crazy. There is a huge complex of dips in the light curve that appear, and they last for like 100 days, all the way up into the Kepler mission's end. These dips have variable shapes. Some are very sharp and some are broad, and they also have variable durations. Some last just for a day or two, and some for more than a week. And there's also up and down trends within some of these dips, almost like several independent events were superimposed on top of each other. And at this time, this star drops in its brightness over 20%. This means that whatever is blocking its light has an area of over 1,000 times the area of our planet Earth. This is truly remarkable. And so the citizen scientists, when they saw this, they notified the science team that they found something weird enough that it might be worth following up. And so when the science team looked at it, we're like, yeah, there's probably just something wrong with the data. But we looked really, really, really hard, and the data were good. And so what was happening had to be astrophysical, meaning that something in space was getting in the way and blocking starlight. And so at this point, we set out to learn everything we could about the star to see if we could find any clues to what was going on. And the citizen scientists who helped us in this discovery, they joined along for the ride, watching science in action firsthand. First, somebody said, well, what if this star was actually very young and it still had the cloud of material it was born from surrounding it? And then somebody else said, well, what if the star had already formed planets and two of these planets had collided, similar to the Earth-Moon forming event? Well, both of these theories could explain part of the data, but the difficulties were that the star showed no signs of being young, and there was no glow from any of the material that was heated up by the star's light. And you would expect this if the star was young or if there was a collision and a lot of dust was produced. And so somebody else said, well, how about a huge swarm of comets that are passing by the star in a very elliptical orbit? Well, it ends up that this is actually consistent with our observations. But I agree, it does feel a little contrived. You see, it would take hundreds of comets to reproduce what we're observing. And these are only the comets that happen to pass between us and the star. And so, in reality, we're talking thousands to tens of thousands of comets. But of all the bad ideas we had, this one was the best. And so we went ahead and published our findings. Now let me tell you, this was one of the hardest papers I ever wrote. Scientists are meant to publish results, and this situation was far from that. And so we decided to give it a catchy title, and we called it Where's the Flux? I will let you work out the acronym. So this isn't the end of the story. Around the same time I was writing this paper, I met with a colleague of mine, Jason Wright, and he was also writing a paper on Kepler data. And he was saying that with Kepler's extreme precision, it could actually detect alien megastructures around stars, but it didn't. And then I showed him this weird data that our citizen scientists had found, and he said to me, crap, Tabby, now I have to rewrite my paper. So yes, the natural explanations were weak. And we were curious now. So we had to find a way to rule out aliens. So together, we convinced a colleague of ours who works on SETI, the Search for Extraterrestrial Intelligence, that this would be an extraordinary target to pursue. We wrote a proposal to observe the star with the world's largest radio telescope at the Green Bank Observatory. A couple months later, news of this proposal got leaked to the press, and now there are thousands of articles, over 10,000 articles, on this star alone. And if you search Google Images, this is what you'll find. Now, you may be wondering, okay, Tabby, well, how do aliens actually explain this light curve? Okay, well, imagine a civilization that's much more advanced than our own. In this hypothetical circumstance, the civilization would have exhausted the energy supply of their home planet. So where could they get more energy? Well, they have a host star, just like we have a sun. And so if they were able to capture more energy from this star, then that would solve their energy needs. So they would go and build huge structures. These giant megastructures, like ginormous solar panels, are called Dyson spheres. Now, this image above are lots of artist impressions of Dyson spheres. It's really hard to provide perspective on the vastness of these things. But you can think of it this way. The Earth-Moon distance is 250,000 miles. The simplest element on one of these structures is 100 times that size. They're enormous. And now imagine one of these structures in motion around the star. You can see how it would produce anomalies in the data, such as uneven, unnatural-looking dips. But it remains that even alien megastructures cannot defy the laws of physics. You see, anything that uses a lot of energy is going to produce heat. And we don't observe this. But it could be something as simple as they're just re-radiating it away in another direction, just not at Earth. Another idea that's one of my personal favorites is that we had just witnessed an interplanetary space battle and the catastrophic destruction of a planet. Now, I admit that this would produce a lot of dust that we don't observe, but if we're already invoking aliens in this explanation, then who's to say they didn't efficiently clean up all this mess for recycling purposes? You can see how this quickly captures your imagination. Well, there you have it. We're in a situation that could unfold to be a natural phenomenon we don't understand, or an alien technology we don't understand. Personally, as a scientist, my money's on the natural explanation. But don't get me wrong, I do think it would be awesome to find aliens. Either way, there is something new and really interesting to discover. So what happens next? We need to continue to observe the star to learn out more what's happening. But professional astronomers, like me, we have limited resources for this kind of thing. And Kepler is on to a different mission. And I'm happy to say that, once again, citizen scientists have come in and saved the day. You see, this time, amateur astronomers with their backyard telescopes stepped up immediately and started observing the star nightly at their own facilities. And I am so excited to see what they find. What's amazing to me is that this star would have never been found by computers because we just weren't looking for something like this. And what's more exciting is that there's more data to come. There are new missions that are coming up that are observing millions of more stars all over the sky.